Welcome back, dear students. In the last session we studied Pythagoras theorem and another theorem connecting Pythagoras theorem, that is theorem 6.7. In today's session we are going to solve few more questions based on Pythagoras theorem. So before we go for the exercise 6.5, let's recall what we learned in the previous classes. Pythagorean triples or Pythagorean triplets. Hope you remember you have studied in lower classes about Pythagorean triplets, so it's nothing new for you. So three numbers form a Pythagorean triplet if they satisfy the Pythagoras theorem. The condition hypotenuse square is equals to base square plus altitude or height square. Okay, so what is the hypotenuse here? Hypotenuse is 5, that is 5 square is equals to base is 4 and height is 3 square. So 5 square gives you 25, 4 square gives you 16 plus 3 square is 9. So 25 is equals to 25. So I can say 3, 4 and 5 forms Pythagorean triplet. In the same way we have many other Pythagorean triplets like 7, 24, 25, 5, 12, 13, the most common, which frequently comes in different questions, and many more. Okay, this is not the end, there is no end to this, and many more triplets we have. So in today's session we are going to see this type of questions. If three numbers are given like this, how to check whether they can be sides of right angle triangle or not. The sides of triangles are given below. Determine which of them are right triangles. So we have to check whether these three numbers form a Pythagorean triplet. In case of a right triangle, write the length of its hypotenuse. So which will be hypotenuse among these three? The longest. Okay, the longest side will be the hypotenuse. Like in 3, 4 and 5, 3 and 4 cannot be hypotenuse obviously. Okay, so 5 will be the hypotenuse. In 5, 12 and 13, which will be hypotenuse? 13. Okay, 13 centimeter or 13 units. Okay, so the longest side among those three will be the hypotenuse side. Okay, so same thing we have to do now in all these bits. There are 4 bits in question number 1. So first one I'll explain you, then remaining all you can try on your own. So 7, 24 and 25, let us take the longest side as hypotenuse, consider it as hypotenuse. So hypotenuse square, that is 25 square, gives you 625. Then RHS, that is height square plus base square. So you can take any one as height from these two. So I am taking height as 24 and base as 7. 24 square gives you 576 and 7 square is 49. And when you add up these both, you will get again 625. So what do you conclude with this? LHS is equal to RHS. So Pythagoras theorem is satisfied because hypotenuse square is equals to base square plus height square. Okay, or you can say opposite by adjacent also, that you will learn in trigonometry. So which is the longest side in this? 25 centimeters. So that is the hypotenuse. So same thing you have to do in all the 3 bits. Here there is second bit. In this you can see hypotenuse square is not equals to, the hypotenuse square is 64, the longest side is 64 or 8. So hypotenuse square is 64. Height and base, when you do, you are getting 45. So here LHS and RHS are not equal. Okay, the square of longest side is not equal to sum of the square of the other two sides. So we can say that Pythagoras theorem is not satisfied here. Hence the given triangle is not a right angle triangle. Okay, or I can say these are not Pythagorean triplets. Same thing you have to do in the third bit as well as the fourth bit you have to try in the same way. Okay, do them because this can be asked in 1 mark. Okay, these are 1 mark questions. Then going to the next question now, question number 2 of exercise 6.5. This problem also we have done in same thing we have done in theorem number 6.7. Okay, those who are clear with theorem 6.7, they will surely not have any doubt in this problem. So we are going to use the same steps which we used in theorem 6.7. So let's proceed with this question now. It's given that just the name of the triangle is changed here. Okay, PQR is a triangle right angled at P. We can see here the figure. PQR is a triangle right angled at P, and M is the midpoint. M is a point on QR. M is a point on QR such that PM is perpendicular to QR. So we get two right angles here. Okay, we have to prove that PM square is equals to QM into MR. So PM square is this common side is equals to QM into MR. So to get this result, I need to prove these two triangles are similar, that is triangle 1 and 2. I need to prove that 1 and 2 are similar, then I can take corresponding sides in the same ratio and prove it. Okay, so let's write what's given first. PQR, triangle PQR, where RPQ is right angle. Okay, clearly you can see here in the figure it's right angle, and PM is perpendicular to QR. So total how many right angles we have in this figure? 3 right angles. Okay, this is 1, 2 and 3. Okay, there are 3 right angles in this triangle. Okay, so same thing we are going to do like we did in the last session. So we have to prove PM square is equals to QM by MR. If I split it, then I get this ratio, that is PM into PM. Okay, I can write PM square as PM into PM is equals to QM into MR. Okay, so I can get this ratio PM by QM. I can bring this QM in the denominator. PM by QM is equals to MR by PM also. So both the things means the same. Now I'll write the statement of theorem 6.7. There is no need for you to prove the whole 6.7 theorem here. So you can just write the statement. If a perpendicular is drawn from the vertex of the right angle to the hypotenuse, then the triangles on both the sides of the perpendicular are similar to the whole triangle and to each other. So you must remember this theorem statement. So in the last session I explained you one theorem in which I said you, if a perpendicular is drawn from the vertex of right angle, okay, to the hypotenuse, then the triangles on both the sides, that is triangle 1 is similar to triangle 2, and they are similar to the whole. Okay, they are similar to the whole triangle, that is the bigger triangle. This is triangle 3. Okay, there are 3 triangles in this, so all these 3 triangles will be similar. This we proved in theorem 6.7. so again we will not prove it, we can take it directly. Okay, so I can say here that PMR is similar to QMP. This PMR triangle is similar to QMP, but here you have to take this, you have to name this carefully. Okay, you should keep it in mind that PMR, where is the right angle coming in this? Right angle is coming at M. M is 90 degree here. Okay, and QMP, when I say QMP, QMP, where is the right angle coming here? At M. Okay, so M is right angle and M is at second position, so we kept 90 degrees on second place. PMR, QMR, QMP, sorry, QMP. So triangle PMR and QMP are similar. How they'll be similar? Let me tell you that also very quickly. They'll be similar because in PMR you can see this is 90 degrees and this R, okay, or you can directly say it, no problem, because if you try to prove, it goes very long, because first we prove 1 is similar to 3, then we prove 2 is similar to 3. Okay, that goes very long. We prove 1 is similar to 3, then we prove 2 is similar to 3, then we say that 1, 2 and 3 all are similar. Okay, or I can say 1 and 2 are also similar. So that goes very long. If you go step by step, you can directly write that these two triangles are similar. Now after these two triangles become similar, I can say that the corresponding sides are in the same ratio. So you know very well how to write corresponding sides, that is PM by QM, then MR by MP. Take first two letters by the first two letters of the other triangle, then next two, that is MR by MP, and if required you can take first and last, but that is not required here. So now this ratio can be cross multiplied. PM into PM becomes PM square is equals to QM into MR. Okay, hence it is proved. If you are not clear with this, you can refer theorem 6.7 and follow the same procedure and do it in the long method. That doesn't matter. Okay, that is also correct. Let's go to the next question, question number 3 of this exercise. Again we got the same question similar to theorem 6.7. In figure, ABD is a triangle right angled at A. Here we have a triangle ABD right angled at A, and AC is perpendicular here. Okay, AC is perpendicular to BD. So we have to show three different things. One is AB square is equals to BC into BD. Then one more thing is asked, that AC square is equals to BC into DC. Then one more is asked, that is the last one, that is AD square is equal to BD into CD. So these all three are important, and again we are using the same theorem 6.7 for this problem also. So what we did in theorem 6.7, that can be done again here. Let's go for it. So given, I'll write first, ABD is a triangle right angle at A. This is given to us, and AC is perpendicular to BD. So total how many right angles are there? 1, 2 and 3. There are three triangles, three right angle triangles in this. Okay, 1, 2 and the third one is the larger triangle ABD. I can prove these triangles are similar and get the ratios. Okay, first triangle we are proving now. Again I wrote the statement of the theorem 6.7. so triangle BAD is similar to ACB. BAD, this triangle, first triangle, sorry, BAD is the third triangle, is similar to ACB. ACB means first. How this will be similar? BAD and ACB will be similar by AA similarity. You know that very well. Okay, for further clarification you can again refer theorem 6.7 proof of previous session. So these two triangles are similar, so we can say BA by ABC. This should be named as BAD. Let's see the angles also. B angle in triangle BAD, angle B. Okay, and this should not be named as ACB. Okay, this should be named in a different way. Angle in triangle BAD, angle B, and in triangle BCA, I should name it as BCA. Okay, angle B and angle B is common in this. Okay, so triangle 3 should be named as BAD. That is correct. Bad. And triangle 1 should be named as BCA. Now you can see here, don't name it as ACB. BAD, in triangle BAD and BCA, you can see angle B and angle B is common, and two angles are 90 degrees here, that is angle BAD is 90 degrees in triangle 3, and BCA, that is angle BCA is also 90 degrees here. So these two are 90 degrees each. So I can say these two triangles are similar. So ACB we cannot write here, okay, because that will give you the wrong ratio. So BA by BC, now you can see these two triangles. If I name this triangle as triangle BCA, now we'll take the ratio. Let's take the ratio now. BA by BC, the first ratio, then comes first and last BD by BA. Okay, so with this we get, when you cross multiply, we get BA into BA, that is you can write as AB also, that's nothing wrong. So BA into BA becomes BA square or AB square, and BD into BC, cross multiply BD into BC. So finally we get AB square is equals to BD into BC. Now you might be wondering, how do we come to know that we should use 3 and 1 only here? So you can see the parts which are asked in this. The parts are AB is there, then BC into BD, this part. So with this you can understand there is no part of triangle 2 is coming here, okay, there is no part, individual part of triangle 2 coming here. So you can understand it by using this method. So this is the way we have to prove. Naming should be very important, okay, as this naming was wrong, we were not getting proper ratio. So for that clarification I proved it. This is not required, okay, these all steps are not required for you now. Just to clarify, to correct our mistake, I did that step, okay. So naming should be correct. Make sure the angles come on the right positions. If B is common, so B should come first or at last or in the middle, okay. Here B is coming first, so here B is coming first. Then A is right angle here and C is right angle here, so they are coming on second positions. So you have to name the triangles correctly, then only you get the correct ratio. If the triangles are named in the wrong way, then you get the wrong ratio and you will not get your result. So this is the way you have to proceed with the next also. In this we are proving triangle BCA is similar to triangle ACD. These two triangles are similar, and in the next one we are proving triangle DAB, that is the third triangle, similar to the second, okay. So there are three triangles I said you. So we prove two triangles are similar by A similarity, or you can directly write the name of the triangle and get our desired results. So hope you all are clear with this. Practice it practice alone can make you perfect in these concepts, okay.